To Welcome back. Today in our probability course, we're going to look at the notion of confidence intervals. And it admittedly takes a while, at least in terms of the formulas and whatnot, to dive right in. So we'll proceed at a more reasonable pace. As usual, I want to bring up some jargon or terms that we've encountered so far. So remember that we have in statistics a difference between what we call in a sample and a population. And I simply say that we survey a relatively small sample to understand a much larger population. And also, we've spent some time talking about estimators. And the reason being is to know when we, as scientists, are justified in going from that small sample to the larger population. Some of the unbiased estimators that we encountered were the sample mean, x bar, the sample variance, s squared. And I did not talk about it at the time, but what we're going to look at today is the sample proportion, p hat. Now, I don't know about you, but when I was first taking statistics classes, whenever I encountered a big word, it took me a while to understand what it meant or to absorb it. So, just reading off my little definition here, a proportion is literally the percentage of items of a certain event divided by the total number of items. So, in other words, a proportion is the percentage of people who do blank, whatever we're looking at the time. And something we've also encountered was the standard deviation of a binomial distribution. That was this p times 1 minus p and the square root of that. And also, when we were doing the central limit theorem, we saw that the standard error was sigma over square root of n. Thus, putting those ideas together, our standard deviation when talking about proportions will be this formula here. Now, for some new terminology, we're going to hear sometimes scientists talk in terms of confidence, and sometimes they talk in terms of alpha levels. So, in scientific literature, confidence and alpha levels are pretty much complements. They're related by this formula here. Or, more directly, if an experiment calls for an alpha level of 0.05, then that's the same thing as saying that we have 95% confidence. I keep catching myself looking at the webcam, even though the webcam's not working right now. This is hilarious. So, confidence, fortunately, is one of those terms that's been chosen over the years because it fits intuitively with the same definition as in the English language. That is, in some sense, we want confidence in our calculation. alpha levels we somewhat talked about in the regression models. That was very loosely speaking, not accurately speaking, the probability of coincidence, and you want that probability of coincidence to be very small. So personally, I'd like to talk in terms of confidence because it just makes more sense overall. But most scientists were trained in talking about alpha levels. So yeah, I probably didn't make it really clear here, but what we're doing overall today is to try to figure out a population proportion for the entire population, the percentage of them that does something. The issue is that we usually cannot survey every single person in the population. So we're going to try to make an estimate instead, and there's some leeway, give or take. And we form an interval around where we think the population proportion will be. So I have some wonderful ggplot code here that I wrote this morning, which when you sit down and read it, it's probably not going to be too bad, but I'll let you do that later. We'll focus on the graph. Something I skipped along the way in the semester was that the binomial distribution and normal distribution actually related to each other, in that the normal distribution approximates the binomial distribution, so that scientists sometimes prefer to use a normal distribution instead. And when we seek 95% confidence, as you can see in the picture, it's this area in the middle of that bell curve. So the area that I have labeled in blue. That means that the tails, the areas in gray on the bottom left and bottom right, those tails put together form the remaining 5% of the area. By symmetry, each tail has 2.5% of the area. So thus the left boundary here of the blue region, that will be at the 2.5 percentile of what we're looking at. And the right boundary of the blue region, that's 2.5% from the top, from 100%. So that's at the 97.5 percentile. And at the moment, I have question marks at those two locations because for the calculations we're doing today, the main skill is figuring out where that question mark is. That is, what is the z value that we need? In statistics literature, that location that I have as a question mark is called a critical value. And because of the process I had just went over a minute ago, 5% in the tails, 2.5% in each individual tail, the that gets denoted as z sub alpha over 2. Fortunately, the folks who made R wanted to be able to do this calculation or these types of calculations pretty quickly, and command to figure out where that question mark is. Remember, we use Q for quantiles. We're using the normal distribution, so Q norm altogether. And to find that percentile location, we use 1 minus alpha over 2. and we find that the z-score is about 1.96. So for those of you taking a statistics class before, you probably heard of 1.96 or were asked to use 1.96 before. Earlier in the semester, in the homework assignments, I had asked you to find a range rule of thumb, mean plus or minus 2 standard deviations. The 2 was a rounding of this 1.96. So as the folks in chat had asked, when we go backwards, if we plug in z equals 1.96 in this way, that area in between z equals negative 1.96 and positive 1.96 is 95%. It might sound like there's a pause in the video. I'm reading questions in the chat. My roommate is currently using a blender to make kind of like a Vitamix mix, so hopefully it's not being picked up on the mic. All right, so we're gonna also be building something called a margin of error. And conceptually, what that is that we're going to multiply the number of standard deviations that is found with the z sub alpha over 2 that we briefly mentioned above, and the sizes of a standard deviation that we got from earlier lectures, namely the sigma over the square root of n. So the margin of error is multiplying both of those notions together. Now I think I do have an image of margin of error. Let me see if I can bring that up. So here I grabbed a political image from a few years back. This was a poll in the leading up to the election of 2016, as you can see, done in North Carolina. So the idea was you don't have a completely accurate or deterministic sense of how the election will unfold in the future. Well, it's at the time the future November. So what you do, of course, is you sample a smaller population, say about 200 people, and you get a sense of how that sample would vote. And as you can see, 38% were polling or saying that they're going to vote for Clinton, 40% said that they were going to vote for Trump, and 9% for a write-in candidate named These Nuts. But because you know that from the time of the poll to the real election in November, the results might change a bit, maybe mostly because the larger population of North Carolina would take place in the election. there's a notion of margin of error, and you can see that at the bottom of the image. So the margin of error is plus or minus 3.2%. And what we are looking at right now in our math class is how to calculate that margin of error. So then finally, what the confidence interval is we take our sample proportion p hat, give or take that margin of error, so plus or minus e. I think I'll take a breather here. Welcome any questions from the folks in chat. So the question in chat is the formation of the margin of error. It's this z-score, which is found in our R code with this code up here, q norm of 1 minus alpha over 2. And in the setting, we have this standard deviation, the square root of p times 1 minus p over n. So we're multiplying these two items together. The question in chat is the margin of error always denoted E? No, it's not always denoted E. I just find it to be easier here. Admittedly, in my current class, this is Math 32. It's an abusive notation because E, unfortunately, was expected value. I also used it for sum of squared errors in linear regression, and now I'm using it for margin of error. If I was writing a book, I would be much more careful about that. But unfortunately, that's what makes reading a math book kind of annoying at times when an author decides to use different notation for every single concept in the book, and then they start to use stuff like let pi equal this, which is still kind of bad. Alright, so now with some of the theory out of the way, let's go into an example. Go ahead and read off this sentence here. So, reading it again. In a survey of 32 UC Merced students, 25 of those surveyed reported visiting campus memes pages. Build a confidence interval for the proportion of UC Merced students that visit memes pages at a 95% confidence. So that is to say, at our university, there are about 8,000 students. If we wanted to survey them about anything, it would be cumbersome. It would be too troublesome to survey everyone. But if I have just a small group of students, let's say 32 of them, I could survey them fairly well. And I didn't prove it, but if we're talking about percentages or proportions, we are allowed to go from the sample to the population as an unbiased estimator. So a question that came up in chat is a little bit more about the notation. So here, we're going to have an alpha level of 0.05. So referring to the bell curve, the normal distribution I showed before, the right hand boundary is that we're looking for the 97.5 percentile. Then the critical value is the z-score that's at that location. Namely, though, approximately 1.96. Question in chat was about order of operations. The division came first, that's why I didn't bother with the extra set of parentheses. A question in chat is why is alpha 0.05? It's actually at the discretion of the scientist. 95% confidence, which is the same as alpha equals 0.05, tends to be used the most in science. The exceptions might be when you have to be really, really careful about something, say nuclear engineering, and you need to be even more precise about things. All right, so back to my example, 25 in the survey said that they visit memes pages out of 32 total. So proportion p hat is literally forming that fraction, 25 divided by 32. Just as a side note, there are probably some functions that do these calculations, and we could write a function ourselves. But I wrote my code this way just to be more in line with explaining the material, so that it's easier to read. In other words, this is not the most efficient way to write the code. It's just easier to read. All right, so from the above formulas, here's how we calculate the margin of error. We once again take that z sub alpha over 2, which is this left factor here, times the standard error, which is this right factor here. Being careful with the 1 minus p hat this time around, putting that in parentheses. And then finally, a confidence interval is literally an interval of numbers. So if we were writing this out by hand, it would be like your usual interval, like when we ask you to write like a domain or range notation with the open parentheses. The lowercase c in the R programming language means concatenate. Sometimes I tell people it simply means we're going to combine numbers. So C for concatenate or combine. And here, as you can see, it's p hat plus or minus e. And we'll get these two numbers here. Now, again, the notion is that it would have been too cumbersome or troublesome to survey everyone in the UC Merced population. We don't actually know what percentage of UC Merced students visit memes pages, but what we're trying to do is form an estimate or a guess and try to hone in or zero in on it a bit. So the way we anal retentive mathematicians describe these results was a sentence like this: we are 95% confident that the true proportion of UC Merced students that visit memes pages is in between 64 and 92%. And I'll take a breather here. Welcome any questions from the folks in chat. So yeah, I did those calculations pretty quickly. Let me expand upon them a bit. So in the polling example, the p hat was 25 over 32, or about 78%. And then in this simple example, the margin of error was about 26%. So for what I was looking at in my hypothetical example, the confidence interval is 78%, give or take 26%. But what you'll notice is that in this formula for the margin of error, this n, this sample size n, is in the denominator. So the implication is that as n increases, your margin of error decreases. In other words, at least according to the theory, the more people you survey, the better your confidence interval gets. So the question in chat is then what's the good margin of error? And it's actually the trade off that happens in reality. I mean, you probably want a margin of error about plus or minus 2%. But if you're surveying people, there's literally cost in time and money. Can you pay someone to conduct your survey? How much time do you have to conduct a survey? And also, there's hassles such as when you approach people to ask them questions, some people simply are too busy or whatever to take part in your survey, or depending on how maybe controversial your survey questions are, it might be difficult to find volunteers in the first place. So it's very what we call domain specific. If you're doing political polls, I'd hope for a margin of error about plus or minus 3%, like you saw in the example. But it depends on what you're studying. Okay, so when we read off this sentence, we'll read it again. We are 95% confident that the true proportion of UC Merced students visit memes pages is in between 64 and 92%. Unfortunately, because of the way the theory rolls out, we have to be that careful when we describe a confidence interval for scientific purposes. So what I'm going to do here in these next, say, 10 minutes or less is to give you an overview of why this is so complicated. So like I've been having my students do in the explorations, we're going to run through a simulation. We're going to use the uniform distribution between 0 and 1 because we know in this controlled experiment that the mean would have to be zero 0.5 or 1/2. For now, we'll stick with 95% confidence, which means an alpha level of 0.05. We once again have our population mean at 0.5. What the simulation will do is draw 10 random numbers at a time from the uniform distribution between 0 and 1. And then we'll do that 32 times. I have a for loop and some other code to build the confidence intervals. Oh, I should also mention I'm talking about averages now, not proportions. This will be repeated in the next lecture as well. So we'll see in the next lecture the margin of error formula is a little different. And I'll connect all those numbers as usual in a data frame so I could ggplot and visualize it. Another question in chat is to define meme. I probably won't be able to do so right now, but as a side note, I'll tell you students that I have tried to design a class so that we could spend a whole semester, the students and I, studying memes. The effects on society, how to design a good meme, the communication, the ethics, etc. But at UC Merced, I got really close, but I could not quite get the class approved. But I tried. Yeah, to study memology. Yep. And a comment in chat is, well, Berkeley has a class like that. Berkeley has a system where you can have like unofficial 1 unit classes. That's why it's a little easier to do there. what I was trying to do at UC Merced is to try to have an official 4 unit class. That's why it was harder to get it approved. Another question that came up in chat was about the distributions. Today we were looking at proportions p hat, and due to some theory that I admit I skipped, that was done in the normal distribution. What we'll look at in the next lecture, when talking about averages and means, that will be done in the t distribution. In other words, there's kind of a scientifically accepted set of standards about which distribution we use. So let me finally show you what this graph looks like. Each one of those horizontal black lines is a confidence interval. That is an interval of numbers that was formed in the simulation. That is, each iteration we picked 10 random numbers, found a mean, built a confidence interval. The red line in the middle is the true answer, the true mean that we knew in advance would be 0.50. What happens is, in theory, depending on what our sample is, depending on what the survey results are, these intervals can change. And the intervals themselves have a distribution and act probabilistically. So it's not completely apparent here in my simulation, but the idea is that over many of these intervals, approximately 95% of them should cross that red line, should contain that true answer. So because all this is happening in the background in our math theory, that's why scientists use a phrase like, we are 95% confident, because of what happens above. Sometimes a confidence interval does its job right, sometimes it does not. So we are only 95% confident as opposed to 100% confident that the interval contains the true population mean. And I'll leave the rest as kind of reading for later. But because of the way the background theory works, one has to be very careful in describing confidence intervals. So there are easily ways to incorrectly describe them as well. So at least what's happening with me as a teacher, I decided to take this lecture that used to be 1 hour long, expand upon it, make it 2 hours long, and I'll essentially do the second half of the lecture next time. But for now, it was great to see you all, and I will see you next time. Bye.